Multiple regression analysis, OLS Asymptotics. Again, read it, large samples. So let me zoom in a little bit and give you the big picture. What do we know so far and what's the difference? What's the plan for this chapter? Okay, so let's quickly summarize these assumptions from the OLS. Assumption number 1, linearity in beta. Assumption number 2, we're dealing with random sampling. Assumption number 3, all the xj's, the variances should be not 0. We need variation in all the explanatory variables. And at the same time, we need to rule out any kind of perfect collinearity, right? So the assumption is no perfect collinearity. Then assumption number 4, zero conditional mean assumption. On average, the unobserved factors should has nothing to do with the explanatory variables. Expected value of u given x should be 0. Again, this was our zero mean conditional assumption. Assumption number 5, our homoscedasticity assumption. We gave these 5 assumptions a name. It's our Gauss-Markov assumption from number 1 to 5. And then we added, so last time we added an assumption. It was a very strong assumption. We said that we don't like this assumption and we have to do something with it. So that's the plan for today. Assumption was, unobserved factor u and all the xj's are independent, and this is the strongest form of independence. They're strongly independent. And then on top of that, the u's, unobserved factors, are normally distributed with average 0 and variance sigma squared. So the first 6 assumptions, we gave them another name. So the name is classical linear model assumption, CLM, classical linear model assumption. Now, why we needed these assumptions? We said that if I have the first 4 assumptions, then my expected, my estimates are going to be unbiased. So we have unbiasedness. It means that on average, we are heading at the target. Then we said if we have the first 5 assumptions, then I can say something about the variance of beta hat j, right? So from this thing, we can understand that unbiasedness has nothing to do with homoscedasticity. Remember, this is only from assumption 1 through 4, okay? But if I have the first 5 assumptions, I can say something about the variance of beta hat j. I can come up with a closed form solution for variance of beta hat j. So having assumption through number 1 to 5, I know what is the expected value of my estimator. I know what is the variance of my estimator, right? But I have no idea about the shape of the distribution of these beta hat j's. So for that, we needed to make assumption number 6. With assumption number 6, because the errors are normally distributed, then we can have some idea about the distribution of the beta hat j. And we said that because this sigma is unknown, so the distribution is not going to be normal. It's going to be t distribution. So now I have everything. We say that having the first 6 assumptions, classical linear model assumption, this is the shape of the distribution, t distribution of my beta hat j. On average, we are hitting at the target, so I have consistency, and at the same time, I have a closed form solution for variance of beta hat j. Okay, so I want you to remember, whatever we discussed so far from day 1 in this class up until today, it holds for any sample size. So this means that for any sample size, if I have assumption number 1 through number 6 for any sample size, then I have unbiasedness, I have a closed form solution for beta hat j. I can rely on the t-stat, f-stat, I can rely on confidence intervals, and etc. And this works for any sample size. Okay. Now, in chapter 5, we're talking about asymptotics. So we want to say something about large sample size, right? And because we're dealing with large sample sizes, we can, so this is the agenda for today, we can relax some of these assumptions. So first, we're going to relax assumption number 4. So we're going to say that we go from zero mean conditional assumption to correlation equal to 0, right? Remember, I'm going to talk about these things in a lot more detail, but for now, remember, in this class, we're going to say if I go from any sample size to sample size which is very large, so if I go to asymptotic sample sizes or very large sample sizes, then I don't need to have this strong assumption. This is my mean independent, right? I only need to have the weaker version of this independence. So So basically, if the correlation or the covariance of unobserved factors and x's is 0, I'm done. So this is, remember, this is a weaker version of assumption of number 4. So this is what we're going to do with assumption number 4. We are going to relax it. And the better news is that assumption number 6, which was a very strong one, we didn't like it from day one, we're going to completely delete this assumption. And so we are going to delete assumption number 6 only if you're dealing with very large sample sizes. So that's the plan for this chapter, asymptotic properties of OLS. Not any sample size properties, asymptotic properties when the sample size is large. So again, we relax assumption number 4, we delete assumption number 6, and then we're going to come up with a new theorem, which is, we say that if I have assumptions from number 1 to assumption number 4 prime, remember the 4 prime is the weaker version, then my coefficients are going to be, how can I minimize this thing? The coefficients are going to be, my beta hedges are going to be consistent. And for consistency, we need to define something called p-lim, probability limit. So we're going to say that the p-lim of beta hat j as n goes to infinity as the sample size increase is going to be equal to beta j. So this is something new that maybe for some of you guys you haven't seen this before. So what is p-lim? This is probability limit. Basically it means that whatever your random variable is, your random variable depends on n. Send that n to infinity and see what will happen to this beta hat j at the limit. So probability limit. Again, we're going to open up all these things today. This was just a big picture of the agenda for today's class. Okay. So I hope you get an understanding of what we're going to do in chapter 5.